So to resume the discussion we were having yesterday, so yesterday we were talking about like how to evaluate different features and see which feature like in some kind of a classification problem, how to evaluate which features are like useful or discriminative and which features are not useful or not discriminative. So like this example we are already seeing, like we discussed in detail yesterday. So what we had done is the class level, which in this case was the ratings given to different products. So there are five possible ratings, 1, 2, 3, 4, 5. But for our convenience, we had decided to binarize it by considering 1, 2, and 3 as low ratings and 4, 5 as high ratings, right? And so then what we are considering is for different values of the features, do the proportion of these two classes, do they change or not? So we saw that for like some features, like for in this case, the if we consider the company feature, the proportion of high ratings under one company is 0.2, but for another company it is 0.55. So there is a considerable difference between these two, like between the proportion of the different classes in the two clusters that have been created on the basis of this example. And we also discussed that this means like at least one of those clusters is relatively homogeneous. That means here like 43 out of 50. So there are initially 100 examples, the different cameras. So on the basis of the company features, these 100 have been divided into two clusters. One has 54 members, the other has 46 members. And this is done on the basis of the feature value. Now, if you consider these 54 cameras, 43 of them have low rating. That is, we can say that 80% of them belong to one class. And which class is that? The low level. So we can say that this is a fairly homogeneous population. And we also discussed that whenever we have a homogeneous population, it is easy to predict the level, because if all of them anyway have the same level, or almost all of them have the same level. So if a new or a new example is added to this thing, to this cluster, we can predict that with a lot of confidence that probably this also has that level only. So like here the idea is basically same as the nearest neighbor idea, that if two things have similar values of features, their level is also likely to be the same, right? So basically what we need to do is we need to choose such features which will be able to split the initial example, the initial set of examples into homogeneous populations. Why homogeneous? So that we can be confident about the predictions that we are making. If you consider this feature, then we see that the like in this class, the it's like 64% of them belong to level L, and 36% in they belong to level H. So you can say that 64% and 36%, I mean 64% is a relatively high number. So you may predict like level L for any example which comes here. But on that, like if that is the case, then if you consider the entire set, that is 100 example, like we had seen that 63 of them belong to low or have low level, and 37 of them have high level, right? So on the basis of that also, you could, like without considering any feature also, you could have just seen that okay, low levels dominate. So if a new example comes without considering any feature, I will just predict a low as the class. That is, I will predict that the customer will give low ratings, because that seems to be more frequent. but that does not seem to be a great idea. So, we want to consider features and see if we can get more confidence than that. And that we will be able to do only if we can get only if we are able to create more homogeneous clusters. So clearly, on the basis of this particular feature, whether the price of any camera is less than $300 or more than $300, it obviously we are not able to create any such homogeneous population. Basically the homogeneity level remains the same as it was before considering any feature. And so basically what we have to do is we have to search for such features which are able to divide the population into homogeneous subgroups, and that kind of a feature is what we call as the discriminative feature. Now the question is how to quantify such discriminativeness of the feature or the homogeneity of a cluster. Okay. So I either one we have we have to try. So the first thing, the concept which helps us to quantify these things is known as entropy. Okay, so now this is the measure of a, this is how entropy is defined in case of information theory or probability theory. Of course, entropy is, as you have studied already for your JE, is also used in physics or thermodynamics. There it may have a different meaning, but in case of probability theory, this is how entropy is defined. So now what information is this actually conveying to you? So let us consider we have two probability distributions. Okay, for the time being, just forget about this classification problem. Let us say that you have two probability distributions. Or let us say that, first of all, let us say that you have a coin. So like the coin has obviously has two faces, head and tail, and it has a bias P. Okay, so P means is the bias, it means the probability that a head will turn up in any random coin toss. So now either now consider the case where P is equal to 0.5. That means what? That means the probability that you get a random toss gives you a head is 0.5, and the probability that you get a tail is also 0.5. Okay. This is, let us say, let us call this as P1. And similarly, there is another bias, another coin with a bias P2, which is like as follows. So here, the probability of getting a head is 0.9 and the probability of getting a tail is 0.1, right? Head, tail. So now if I ask you which coin, if you know this thing, if you know these information, if you know the values of P1 and P2, about which coin do you have more information initially? What will you reply? Yes, the coin which is like what do I mean by information in this case? The information can only be related to tosses, to probable results of a toss. So, that is to say, you may be looking for such information that uh, if I toss this coin, then will I get a head or will I get a tail? Or if I do such number of tosses, then will I get such number of heads or not? These kinds of questions you may be interested in. So, which of these distributions do you think can give you more information before any toss is actually done?
Second.
Second one, right? Because in the first case, when you do a toss, it can be like there is equal probability of head or tail. So basically, you don't have any information at this stage. You can't say anything about what the result of a toss is going to be. But in the second case, you without even tossing the coin, you are almost sure that you are going to get a head only. So in this, we say that in this case, there is more information and there is less information. In other words, we say that this system is random and or more random, and this system is more orderly. Okay. So these are concepts which are frequently used in information theory. Seen in another way, we can also say that the first distribution, this has low discriminative ability. And the next one has the high discriminative ability. Okay, so so now, if you actually calculate the values of this entropy, so how do you calculate? So the formula is saying that there are two possible classes, head and tail in this case, and in each one has a probability. So I define the entropy as, in one case I define it as 0.5 log 0.5 minus 0.5 log 0.5. Okay. So as you can say, like this basically adds up to log of half, which is log 2. So if you are taking log base 2, you will get 1 as the entropy. So in general, when we are taking the log, we can that is, you can it does not really matter. You can take 2 as the base, but usually what people do is they like, if it's a k class classification problem, then they just take the log base k. And if you are so like this is log 2, as taking k equal to 2, this of course is 1. In the second case, it is like minus zero point 0.9 log 0.9 minus zero point 0.1 log 0.1. Right, and so you can just work out the details, and it will probably get some value like 0.47. So like if you consider an extreme case, that is, one class has a probability 1.0 and the other has probability 0.0. So then it's like 1 log 1 minus 0 log 0. Now log 0 of course is not does not make sense, but like keeping that aside, you have to see that it is multiplied by 0 also, so you can just say that this is 0, and log 1 is also 0, so this basically becomes 0. So if this is the, like in case of this distribution, where 1 is 1.0 and 0.0, so here h is said to be is actually 0. So as you can see, in the situation where we have absolutely no information, where it is a completely random system, 0.5, that in that situation the entropy is 1. Then in the situation where both are that is, one is 1 and the one class has full 1 probability and the other class has 0 probability, that is, it's a fully determined system, there is no randomness in it. In that case, the entropy is 0. So so it's like saying that the more the more random is the system, more is the entropy, and more orderly or more homogeneous the system, less is the entropy. So basically, when now let us bring in this idea, this notion, to the case of these clusters which we are talking about. So if we are talking about this kind of like if we have this kind of a situation, so let us say there are I have a data set of 200 creatures. Some of them like 100 of which are cats and 100 of which are dogs. Now on the basis of color, we have like divided them into two clusters, the yellow clusters and the white clusters. So in the now if you consider the yellow cluster, it has 99 examples in it, and the white cluster has 101 examples in it. Now the initial if you consider the initial set of full 200 examples, 100 of them are cats, 100 of them are dogs. So it's like 0.5 in one, the probability of one cluster is 0.5, the probability of the other, sorry, not cluster, the probability of one level is 0.5, the probability of the other level is also 0.5. So this is a perfectly random system where the entropy will be equal to 1. Now I have broken it up into these two clusters or subpopulations. Now, if you look at this subpopulation, so here you can find that like there is hardly any, in this case also there is hardly any difference between the proportion of the two classes. I mean, the probability of the cat class is 52 by 99. The probability of the dog class is 47 by 99, both of which are nearly equal to zero point 0.5. Like maybe one maybe 0.52 and then another maybe 0.48 or something like that. But there is effectively no difference between this. In this case also, that's almost the case. So you can see that the two subpopulations or clusters which we have created on the basis of color feature are almost as homogeneous or as heterogeneous as the original population itself. So we can say now what we do is what we like for any such splitting of the population. So this was the initial population. We have split into two parts. So what we do is we calculate the entropy of the original population and subtract from it the entropies of the subpopulation. Now we also like while calculating the entropy of the subpopulation, we also keep in mind the size of that subpopulation. So the original population was full 200. So the this population, the first subpopulation, its size is 99. So we can say that it is like 99 by 200. The second one, the second subpopulation, its size is 101. So we can say it's 101 by this relative size is 101 by 200. Fine. So now we so original entropy we write this and the split the entropy of the two subpopulations also we calculate like this. Okay. So if a feature, now tell me, if a feature is discriminative, then this quantity which I am calling as information gain, will this information gain be high or will it be low for a, if the feature is discriminative?
Should be high
And why should it be high?
because entropy will be zero for splits.
The entropy need not be zero, but if it like
Close to
close to zero. So the original entropy will be close to one because it's like both classes it will be very heterogeneous, means like different classes will have nearly equal probability. But if the feature is discriminative, then in the subclasses it's like both the different like in both subclasses one level will be dominating. So the entropy will be close to zero, and which means like as you correctly said, this difference will be large. Now original entropy is high. After splitting, both the entropies have become low, so the difference will be large. So when we are considering different features and we are like evaluating which feature is more discriminative, we can basically calculate their information gains and see which feature is giving you the maximum information gain. So that is the idea. So in this case, we saw that the information gain is nearly equal to zero because even after splitting, the entropy remains almost unchanged. But if you consider another feature, let us say the weight of the animals. So in this case, you will see that uh, like in one class, the among the lighter animals, 95 out of 105 are cats. That is nine. There is like one level has probability 95 by 105. The other has only 10 by 105. So this is so here the entropy has significantly reduced. It's only 0.45. Similarly, if you consider the heavier animals, that's also very much skewed. So we have 90 out of 95 probability of one class. So in this case, if you calculate the entropies and multiply them by the relative split size, then what you will actually get is like a very large information gain of 0.62. So unlike this feature where the information gain was almost zero, in this case you have actually got a large information gain. Okay, and why do I multiply this by the split size? So so as I was giving this example, in this example, if you remember, like we had found a pure class, the homogeneous class, of which 80% belong to one like one class level, namely the low prices. However, we also said that there are only 10 examples in this cluster, right? So that is whatever we are. So we basically we do not have so many examples on the basis of which we can make the prediction. So I do not. So even if we get a pure cluster, if if its size is low, then we do not want to give too much importance to it. That is why we when we are considering the entropy of one class, then we also have to consider the size of that class. So otherwise, we could have just like split in the way of one example, that is one single example we could have considered as one cluster and so on, right? So but then each of those clusters will have size of just one, and on the basis of that we will have to say like do the clustering. So that's of course not a great idea. So to ensure that that kind of splitting does not happen, we try to put the that is when we apart from calculating the entropy, we also multiply it by the size of the split, just to make sure that we are not giving undue importance to small but homogeneous clusters, because the ultimate small homogeneous cluster is just a single example. So that's one example will have of course one level associated with it, so you can say that it is pure in a trivial sense, but or homogeneous in a trivial sense, but you cannot really do a classification on the basis of that. So to avoid such trivial kinds of splits, we make like we not only consider the entropy after splitting, but we also consider the size of the split. Okay. So basically what we do is we try to uh, like split the dataset on the basis of such features which will provide high information gain. In other words, the population after the populations or the subpopulations or the clusters after splitting will have low entropy. So in this case, like if you consider that this cat dog classification example, so we decided that we will consider this feature, the size of the animals. So basically the algorithm which we will make is something like this. So initially we have a population which has all the examples in it. Now I will split it according to the this its weight feature. If the weight is less than 15, then like I will predict cat. If the weight is more than 15, then I will predict dog. Okay. So if this is my classifier, then the question is how accurate that classifier is going to be. Of course, for that we need to take an validation set and a testing set and so on. But let us say just on the training set, what its accuracy is going to be. So if you see here, so the for like those animals whose weight is less than 15 kg, all of them are being classified as cat. So if you consider the training set, that is 90, there are total 105 examples in this category, out of which 95 are cats, 10 are dogs. But actually all of them, but when you will predict all of them as cats. All 105 will be considered as cats, right? So that means all the 95 cats here are going to be correctly classified, but the 10 dogs are going to be wrongly classified. So it's like so C95, 95 cats you have correctly classified, but 10 dogs you have wrongly classified. If you consider here, this that is the subpopulations which weigh more than 15 kg. Here there are 95 examples. 90 of which are dogs, but 5 are cats. So all of these are going to be classified as dogs. So that means these 90 dogs you have correctly classified, right? But the 5 cats you have misclassified. So if you now consider what is your performance overall, if you consider only the cat class, there were 100 cats, 95 of them you have correctly classified here, and 5 of them you have wrongly classified here. So for the cat class, your accuracy is 95 by 100. But if you consider the dog class, so 10 dogs here, there are 100 dogs, out of which 10 you have misclassified, you have considered them to be cats, but the remaining 90 I have considered them to be dogs. So 90 out of 100 dogs are correctly classified. And if you consider the overall numbers, we can say that out of 200 examples, 185 have been correctly classified. So this 94 point, sorry, or whatever it is, 92.5%, this is the accuracy of your this decision stamp, which is a reasonably good accuracy. Okay. So now, so this kind of a thing, as I said yesterday, this is called a decision stump. Now, what if you think that the features you have, the subpopulations which you have got after one round of splitting are still not pure enough? Okay, so that is in this, like initially you have a like initially you have a high entropy, then you, after splitting, of course you have split on the identified that feature which gives you maximum information gain. So of course these subpopulations which you have got are, they will have low entropy than the initial population. But what if you think that even these are continuing to have reasonable entropy? So that is to say, if if I do not get good enough split, like if you are not able to find a feature which is good enough for feature for splitting, then what we will do? The answer is that we will continue to split in that case. So 95 cats, so here there are 95 cats and 10 dogs. So suppose you think that this is still not pure enough, this is still not homogeneous enough, so then you, what you can do is you can consider other features. For example, maybe the why not say the color feature. So it's possible that if you consider the color as the feature, say there are only two colors available in the data set, yellows and whites. So these 105 examples, you are now going to split on the basis of color. So if you, there are so you get a subpopulation which has yellow color and a subpopulation which have white color. I'm saying subpopulation because like it's like this is already a subpopulation because they all of them are they have weight below 15 kg. Now I am adding one more criteria. So these examples, they weigh less than 15 kg and have yellow color. These examples weigh less than 15 kg and have white color. Similarly, these examples also. So now if you see here, it's like those examples which weigh less than 15 kg and are yellow, there it seems that there are 53 such examples, 50 of which are cats, only 3 are dogs. So obviously we will predict like the so if a new example comes in like satisfies both of these criteria, that is its weight is less than 15 and its color is yellow, then of course you will predict its class level to be cat. So in the, and this way what you will with respect to the training examples, you have got 50 by 53 correct and 3 by 53 wrong, right? Now similarly, if you consider here, you will also see like 45 are cats and 7 are dogs. Now you may think that this is not that pure or that homogeneous a cluster or subpopulation. So you may continue to split it even further if you wish. Similarly, in this case, you have 46 examples, 44 of which are dogs and only 2 cats. So here you will happily predict dog, and that way, like in the training set, you have made like got 44 correct and only 2 wrong. Here also the same situation, that is you have got 46 right and 3 wrong. Yes, and so on. So, so now what is your accuracy now, or how many mistakes you are making? So here you made 3 mistakes, 3 dogs are there. Here you are making 7 mistakes, 7 dogs are here, so total 10. Here 2 mistakes, because so 12, and here 3 mistakes, that is 15. So total 15 mistakes you have made. So the curious thing to note is that here you made 15 mistakes. Here also you are continuing to make 15 mistakes. That means, like, this second round of splitting has not given you any great advantage so far, right? So it's so so now you can do two things. Either you can decide that this is not giving me any extra benefit, so why will I split, even consider this split? That is, if one, like if considering one feature is enough, then why should I consider two features if it is not giving me any extra advantage? So what you may do is you may just leave out this level. So you can just revert, just drop this and just revert back to the start. That is one thing which you can do. The other thing which you can do is notice that this is the place where you have made maximum number of mistake. There are 7 mistakes here. The other 3 have total contributed to only 8 mistakes. So if these you are able to somehow reduce, then it's possible that the total number of mistakes may come down from 15 to maybe 11 or 12 or something like that. So what you may do now is to consider further features apart from x1 and x2. Say, like if there are other features available, see if there is any other feature which can give a more pure or more homogeneous split than this. Okay, and then on the basis of that, you will have to do the classification. So it's like saying, so suppose there does exist a feature. So then what will happen when you are doing the new classification? I mean a test classification. So a new example comes, you first consider its weight. So suppose the weight comes out to be like less than 15 kg. So then you consider its color. So if its color is yellow, then you predict it is a cat. But if it is white, then you consider another feature, and then based on that feature you take the decision. So this is the way, like, we can use the decision tree. So basically what's the, so and when to stop. So or till how long will you go on splitting? So there are like there are two possible criteria for splitting. Either you can stop splitting when you see that no feature is giving you any further information gain. That is the information gain you that, or the entropy of the population before splitting is basically equal to the entropies of the subpopulation after splitting also for all features. If that is the case, then there is no further split to be made, right? That is one way you can stop the criteria, or you can stop the splitting. Or in like inside, or you may split if or you may stop splitting if the maximum tree depth is reached. So you may already have some predefined tree depths, say that is I will not consider more than 2 or 3 features, or more than 1 or 2 features. So if you have already reached that level, then you can stop. Okay. So, so intuitively, do you have some idea about why we should stop beyond a particular point, and why we will not just go on splitting further and further?
Sir, it might end up overfitting to the training data.
Yeah, exactly. It may end up overfitting. That is just to explain that in more simpler language. So if you go on splitting and splitting and splitting and further splitting, with every split you are basically creating smaller and smaller population, right? So in the extreme case, you will reach such a situation where like every single example will that is like the subpopulation will you will get each subpopulation is just one single example. If you like, of course that depends on if so many features are available or not, but in the extreme case you will end up like creating one subpopulation for every single example. If you have n examples, you will get n subpopulations. But or even if it is not like that, even if it does not reach that extreme, the subpopulations which you are getting will keep becoming smaller and smaller and smaller. And as we have seen, it's like even if a subpopulation is very pure, then but if it is small, we usually do not want to take a decision on the basis of it, right? So why uh, like again that is because of overfitting. In a sense that is like a case of overfitting. So I do not want to do that, so I will stop the splitting beyond a particular level. So if we want to put the whole thing in a nutshell, that the whole algorithm that we discussed in a nutshell, the decision tree algorithm. So the first thing is you have the full population, you have all the features. So now you identify the feature that results in maximum information gain, and you split the dataset accordingly. Now, once you have for a like consider those split sets or the subpopulations, identify if any feature can result in further information gain on these subpopulations. So, it may happen that some subpopulations can be split further, some cannot. It's possible that, like in this case, in these three subpopulations, there is no further split to be made, or there is no feature which gives a more pure cluster than this. But in this case, uh, in case of this subpopulation, it may be possible to split it even further to create more homogeneous subpopulations, right? So in that case, it is okay if you do not split any of these subpopulations or subpopulations, but you do split these subpopulation. So so it is not necessary to for the tree to be balanced. That is, it's not necessary to have that all these nodes should have equal number of children. So it's possible that these three nodes will become the leaf nodes, while this node will produce two more children. That's okay. So whenever for any subpopulation, when you see that so there is a feature which can give you more information gain on the split sets, you can split it. But if there is no such feature, then you stop, and then you just repeat these steps. You just go back to 3 and continue to see that whether the like there is any such feature according to which you can split it further. Of course, if there is a maximum depth level already specified that I will not split more than thrice or more than twice, then once that limit is reached, then of course you will stop. And so finally you will get, once you have stopped the splitting, then what you have got are the leaf nodes of the tree. So like which are so these are called the leaf nodes, which are the smallest populations with the smallest subpopulations which you have produced. These are called the leaf nodes. And so each leaf node will have different the examples in each leaf node will have different labels. So I will find which is the modal or the most frequent level in that subpopulation, right? And so this leaf node will be associated with that particular level which is most frequent in it. So here, if the cat level is most frequent, this leaf node will be associated with cat, and so on. So this is so at the testing stage, whenever a new example appears, you just follow the sequence of decisions based on its features, and and you just keep on moving it through the different subpopulations till it reaches a leaf node, and whichever is the modal level of that leaf node, you just associate that level with your testing examples. So just to give a demo, so suppose this is the tree which you have built for the cat dog classification, and now you get a new example which is like for which the color is white and the weight is 12. So the weight is 12, so it comes under this subpopulation because like basically in here you see which of these criteria is satisfied, whether its x2 is less than 15 or more than 15. X2 is 12, so it comes here. Then you check its color, whether the X1 is white or X1 is yellow. So in this case, it is white, so it comes to this subpopulation. So this subpopulation here, its modal level is cat, so you make the prediction as cat. This is the way you make the classification with the help of decision tree. So this has the following advantages. First of all, it is easy to interpret. It is easy to classify at test time, and it provides a ranking of the features. That is, it tells you which features are more useful and which features are less useful. That is something that is an useful thing or an useful byproduct of this decision tree classification. And the testing is also very easy. You just have to evaluate one feature after another, and accordingly just move your example through the different subpopulations or different nodes of the tree, and whichever leaf node you reach, you just make the prediction accordingly. So basically the runtime complex, the test time complexity is just like in the order of the depth of the tree. So if the tree has depth 2, you just need to do two sets of operations. And however, it has some disadvantages also. The first disadvantage is that no optimal solution is known. That is, we have decided to split this tree on the basis of entropy or on the basis of information gain. But so what? So is there any mathematical basis of choosing that entropy as the ideal feature, or can we give some kind of a theorem which says that if this is the if this is the process you follow, then the clusters which we will get are as pure as possible. You cannot get a more homogeneous cluster than this. Can such a result be given? Probably not. So we do not. So it's basically what we have done is basically something like a heuristic, like a greedy algorithm. At every step, you are doing what seems to be the best thing to do optimally, like at that point. But is that going to give you or bring you to some kind of a global optimum solution, or the split sets which you have got, are they as homogeneous as any other split set? Couldn't we have split the data set in some other way? We should have been even more homogeneous than this. So these are not questions which we can answer with this algorithm. So no optimal solution is known. And as we saw earlier, that if the tree just keeps on going overfitting, then it can overfit. Sorry, I mean, if you just keep on growing the tree deeper and deeper, it can result in overfitting. So we need to stop the growing. There are many other practical disadvantages also apart from these. That is, what are these splitting criteria going to be? So here, if the variables are, if a particular feature is categorical, then of course there is less to be said about it. So every value of that categorical variable you will have to consider as a subpopulation. So if you are considering the color feature, it's a categorical variable which can take maybe 2 or 3 or 4 or 5 values. So you'll have, if for each value you can split them. But the bigger problem is with numerical features like say the weight. So in this case, we have decided to split the weight at 15 kg. That is less than 15 or more than 15. So why did I choose this 15 kg as the split as the cutting point and not say 8 kg or 23 kg? So, so you may say that if I had taken considered something like 8 kg, you would have like we would have got unbalanced classes. That is, one will have less examples, the other will have more examples. But it's possible that you would have like the like even those classes which you would get like that, maybe they will still be like as pure or maybe even more homogeneous. So does it mean that I should actually consider all possible splitting points and see which gives you the maximum information gain? I mean, that is going to be really cumbersome, especially if there are a large number of examples and like if like x2 can this feature can take so many different values, like, right? And we have seen like in yesterday's camera example also we had seen this kind of a situation where if you consider whether the 300 as the threshold for price, we in this case we had got very less information gain. But if you considered 500 as a threshold, this time we got slightly better information gain. Not great, but still at least better than this. So then, so, but why, how did we come across these numbers 300 and 500 in the first place? Why did we not consider, say, 400 or 250 or anything like that? So there is really no answer to this. Either you can consider the median value or you can consider the 80 percentile or something like that you can do. But again, these are just heuristics which you have to do. There is no guarantee that any of these things will give you the best possible answer. So some level of arbitrariness of human judgment is always involved in this. So you will so that in other words the algorithm is intuitive but it's not really foolproof. And now finally one more word before concluding this topic is that this can also be used for regression problem. So regression, as you know, is a situation is a supervised learning problem where the output which you get are not discrete levels but continuous or values. The real numbers are output. Okay, so these kinds of decision trees, they are sometimes also called as CART. CART as in classification and regression trees. So C stands for classification and R stands for regression. That is the same framework. With the same framework, you can like you may want to do the regression. However, there is a problem that is the question is like if we are dealing with real valued output levels, then how will you calculate the entropy? The entropy you are calculating because like so basically you had some kind of a probability mass function. The probability mass function was defined on what? On the labels. So here are two labels. So like in one probability, one class had 95 by 105 probability, the other had 10 by 105 probability. So you could define the entropy the way it was we had defined it in this case also. But if we are dealing with real numbers, then you will not be able to get these kinds of gross numbers like 95 in one class and 10 in another class. You will just see lots of now like 105 examples, maybe all 105 will have different numbers, right? So, so in such a situation, if we have so many different levels, so many different values as the levels, in that case, entropy obviously is not going to work. So can you suggest something else which will work in such a situation? Entropy, what is entropy giving you? Entropy is basically giving you a measure of uh, how homogeneous the system is. Right, so now if you have real values, if you have a large number okay, so let us consider two examples. In example one, these are the values you have got: 1.1, 2.3, 1.5, 0.7, minus 0.2. This is like these are the values which are present in one subpopulation. In the other subpopulation, the different values you have got are say 1.1, 5.5, uh, 13.3, minus 17.4, and 0.5.
So standard deviation or variance.
Yes, yes, right. So in this case, like as you can understand, this one you will consider as a more homogeneous system because this has smaller or less standard deviation or variance, and this one has more. Right. So in this case, when you are dealing with regression problems, the thing which you will the feature that you will consider, I mean the criteria which you will consider for homogeneity will be the variance of the levels instead of entropy. And similarly, when you reach a leaf node and when you actually have to make the prediction, so here you will not find a the like a the most frequent level or something like that. Again, if there are in that case, if there are 53 examples, 53 of them will have different 53 different values, but those values will all be close to each other. Why? Because you have chosen the features which reduce the variance. So then, if you have a large several numbers which are all close to each other, you can easily represent them by the mean of them. So the final value which you will which you will predict at each leaf node will be the mean level of the leaf node instead of the mode, right? That is the way you can use a regression tree. So here is an example. So we just flip back to our camera example which we are dealing yesterday. So like there are, so let us consider two features, the company feature and the video rate feature. So if you consider the company features, there were 100 total 100 examples, which 54 of them in company 1, 46 of them in company 2. If you consider the company rating, the mean ratings of company C1, it is 3.0, mean rating of company C2 is 4.0. So, and if you if you consider the full population without consider splitting it on the basis of company, the mean level is 3.46. Now, if you consider the variance, you like in case of for the examples under company 1, their variance is 1.5. For those examples in under company C2, their variance is 0.5, whereas the original variance was 1.1. So it seems that if you consider the company C1, the variance has actually increased from 1.1 to 1.5. That is, it is at the this subpopulation is actually more heterogeneous than the original population itself. But this subpopulation is considerably more pure homogeneous. This has a significantly less variance. So overall, am I gaining or losing? So to quantify that, you have to calculate the reduction of variance, which is the analogy of the information gain in this case. So original variance 1.1, the split variance are 1.5 and zero point 0.5, which you have weighted according to the relative sizes of the two splits. So this is the like your reduction of variance 0.06, which is actually quite small. But if you consider video rate as the features, then here these are the numbers you will get. So the original variance was 1.1. In for the cameras which have low frame rate, their variance is also is 1.2, which is just about same as what it was earlier, slightly more. But if you consider the cameras which have high frame rate, their variance is small, zero point 0.4, and their mean is significantly higher. That is, the mean was originally 3.46. In this case, it has dropped partially to 3.1. In this case, it has improved considerably to 4.5. That's a big jump. So that means that like this is slightly impure, but or heterogeneous, but this is quite homogeneous. The only catch is that this has 70 examples while this has 30 examples. But so if all these factors are taken into account for calculation of your reduction of variance, you will find that 0.14 is the reduction of variance, which is not a bad thing. That is, from it was originally 1.1. From that, the combined variance has come down to 0.887, which is a reasonable, or yeah, which is a reasonably good reduction, right? So between these two features, clearly the second feature, namely frame rate, is giving you a bigger reduction of variance. So you will use that as the criteria for splitting. So that is your regression stump. Of course, you may think that this feature, I mean this subpopulation is still not uh, uh, this is pure enough. So you may want to continue to split it further. So this way you can this is the way you can do the regression. So note that so here I am no while predicting the ratings, here I am considering the output rating to be 1, 2, 3, 4, 5. I'm considering this as a regression problem now. I'm no longer considering it as a classification problem where there were two levels with low and high. So here I am actually considering the values of the different levels. Okay, so that is the basically the decision, the classification and regression tree algorithm. Using this, we can do both classification or using if there are like if we are doing when we are dealing with discrete levels. So on the basis of information gain, entropy and information gain, we can do classification. But if it is a regression problem having real valued levels, then on the basis of variance and reduction of variance, we can do the regression problem also. Okay, so that brings us to the end of this. But as we saw that this has various drawbacks also. And so the most important drawbacks are as follows. That is, it is like after all, it's a heuristic. It's not guaranteed to give you any kind of optimal solution. And there is a practical problem also. That is, we do not really know what the splitting values should be. Like even if you consider a feature, at what value you will split that feature, or whether you will split that feature into two subpopulations or three or four subpopulations, these are like there is no clear answer to that. It ultimately depends on you. Okay, so this is the decision tree algorithm. Now we will take a 5-minute break as it is 9 o'clock. After that, we will move to another topic. Okay, welcome back. So let us so far you have come across so many different kinds of classification algorithms, right? You have seen the nearest neighbor classifier. You have seen neural network classifiers, naive-based classifiers, decision tree classifiers, and so on. So now, when you are given a particular data set, we like you would have understood by now that there is no classifier which is like which will uniformly do well over all the data sets. That is to say, no classifier is inherently better than other classifiers. You can always construct a situation or construct a data set or construct a set of features where like where you can make your favorite classifier win. And this is true for any classifier. So that is to say there is no classifier which is inherently better than the others. Even among the same class of classifiers, say suppose nearest neighbor, you are considering let us say k like k equal to for different values. So suppose you have three versions of nearest neighbors classifiers for which one k equal to 1, another has k equal to 3, the third has k equal to 5. So you again on a given data set, you cannot say for sure which of these Ks will work. So you know the advantages and disadvantages of the different values of K, right? So that is so can you tell me what like what are the advantages of taking low value of K and what are the advantages of taking high values of K?
Low value of k will be more generalized, but like it will be underfit if low value of k. If high value of k, then it will be overfit.
So can you instead of talking about underfitting, overfitting, can you give some concrete situations where it will be having low value of k is good and where some low value of k is bad? So why did we from k equal to 1 from the pure nearest neighbor? Why did we go to k nearest neighbor in the first place? What was the problem with k equal to 1?
Because there might be more noise in the data which might affect our results.
Right. What you really mean is might be outliers. That is the when you are considering when you get your test point and you are comparing its distance with the different training examples, it's possible that the nearest neighbor which you have found is actually an outlier. And what do I mean by an outlier in this case? By outlier, what I mean is an example whose label is different from what it should be if we go by the broader trends of the data set. So if you are that is say if you consider a cat dog classification problem, so you find that the most of the cats have low weights of around 3-4 kg and most of the dogs have high weights of about 15-16 kg. But now we have got a classification a test example and you measure its weight to and compare its weight to the other examples of your data set. So suppose you find that it is its its nearest neighbor is like is some is like an animal with a low weight, but that happens to be a dog. Maybe it's like basically a small puppy, so that's why it has low weights. So it is but its level is still dog, so you will end up classifying your test case as a dog. But you have done it on the basis of what is essentially an outlier, so that is not a great idea, right? So I will so to avoid the presence of such outliers, I moved from k equal to 1 to higher values of k. But if I consider high values of k, then what happens?
We might end up considering such data which is not at all related to our test data.
Exactly. That is, we may end up like if you consider say 7 nearest neighbors or something like that, we may some of those neighbors may not actually be neighbors at all in the first place. So they like, of course, they like there are various variants you can come up to prevent such situations, putting some threshold on the distance or inverse weighting the different neighbors and all these kinds of stuff. All this you can do, but but the basically there is no like there is nothing which about which you can say it is foolproof. That is, for every like every version of the algorithm, you can come up with a data set or a set of features or something where it works best. So what people do is, instead of depending on a single classifier, people consider multiple classifiers. That is, it's like instead of depending on like, of course, the different classifiers might give different examples, but instead of depending on only one classifier which will give a single result, you just consult different experts. Even if their opinions vary, you can just take the which is the most common opinions. You can do something like a voting. If it is a regression problem, then the voting is very easy. You just like take the mean of the different predictions. And if it is a classification problem, then you can consider the mode of all the predictions. That is, which prediction is most common. Right? So so this is a simple voting scenario. So suppose there are three possible class levels, 1, 2, and 3. Now, and you have 6 different classifiers, F1, F2, F3, F4, and F6. So if you, these are the different levels from the different classifiers. So what you do is essentially you take votes. You see how many votes the level 1 has got. So you see that F1, F2, and F4 have given level 1. So it has effectively got 3 votes. Similarly, level 2 has got 2 votes and level 3 has got 1 vote. So you can understand that level 1 is the mode of all these predictions. It has got 3 out of the 6 votes. So it's your final prediction is y equal to 1 in this case. That's what you call as the simple voting. Now, why am I saying simple? Because we have just considered that all these classifiers, like I have given them equal weightage. But what if these classifiers are not equally reliable? It's possible that some of them are like on the kind of task which you are solving. It's possible that you have found that some are doing better than the others. In that case, you may want to give some kind of a weightage to the different classifiers. Now, how those weightages will come, that's a different issue. But as of now, let us say that like we are associating different weightage to the different classifiers. So let us say that these are the weights we have given to the different classifiers on the basis of some performance on some benchmark dataset. So then what you do is, when you are taking the vote, instead of taking the simple vote, you take the weighted vote. That is, for every class, instead of simply counting how many classifiers have predicted that class, you just add up the weights of the classifier which have predicted that class. So for example, in this case, for class 1, you see that the 3 classifiers have predicted class 1, but if you add up their weights, you get 70. In case of class 2, you find that only these 2 classifiers have voted for class 2, but both of them are very reliable. Both of them have 9 weightage. So their total weight adds up to 80. So in this case, even though 3 classifiers have predicted class 1 and only 2 have predicted class 2, but those 2 classifiers are more reliable than the 3 classifiers taken together. Right? So that's why in this case, our prediction is going to be 2 if we take the weighted prediction. So like so now the question might arise that where will all these classifiers come from? So they may come from different ways. One is, as I was trying to say earlier, you have the same training sets, but you just use the different classifier functions. You that is that is you have three k nearest neighbor classifiers, one for k equal to 1, another for k equal to 3, another for k equal to 6. Then you have a neural network, and another you have another neural network maybe with a CNN kind of layer. That is, your first neural network has only fully connected layers. Your second neural network is a convolutional neural network, and maybe along with it you have a decision tree also, and so on and so forth. So that is one way, that is basically you are using different classification functions for the same data set. Other thing which you might do is you split the data set itself into multiple parts and train a classifier on each of the parts. Those parts might slightly overlap, but that's okay. So basically your different classifiers are, it may be the same classifier function, but you are focusing on different parts of the data set for this. Another thing which you can do is you can consider different subsets of the features, and for every subset you can train a classifier. So once again, there is no scientific basis of saying that any of these are better than the others. These are all things which people do in under different situations. But why is this good? Like, what is the logic of doing this? One is, it is found like these kinds of things are found to reduce the overfitting. It also like reduces the variance of the predictions. Right? Variance means what? Variance is like bias and variance you may have come across at some point. So variance, like a situation where there is high variance, basically means that examples which have similar feature vectors can be classified with like different labels. So that that is, or that is, the predictions are vary significantly, even if the features don't vary so much. So that is that's basically the idea of variance. So we find that if we do this kind of thing, then such variance reduces. Of course, bias may still be there. So bias is basically, if you, whether the, like if you are making many predictions, is the mean prediction away from the how much, like is it close to the true value, or is it away from the true value? The difference between the mean prediction and the, I mean the mean of your different predictions and the actual value, that is called the bias of your prediction. So there are two things. One is the bias and the other is variance. The bias is basically saying how far apart your predicted value is from the original value, and the variance is like how are your various predictions different from each other. So if I consider let us say that your true value, the true value is this thing, and the thing which you and what you have predicted, like they are like this. Okay, these are the different predictions which your different predictors have made. So you can see that the mean value of your different predictions may be something like this, which is far away from the mean, from, I mean from the actual value. So that means there is considerable bias, and there is also significant variance among the different predictions which you have made. So this is a situation where you have high bias and high variance. Then you may or you can consider an alternative situation where you have that your the predictions, different predictions which you have made are something like this. So the mean of your different predictions is this, whereas the true value is this. So the bias is still there, but at least the variance has come down in this case. Like at least you are being consistent in what you are saying. So this is a case of high bias, low variance. Similarly, there may be situations of low bias and high variance. That is to say, the predictions which you have made are somewhat like this. Right, so if you take the mean of these predictions, you will probably get something like this, which is very close to the actual value. So the bias is low, but but note that none of the predictions have actually come close to predicting the true value. They like the predictions are still all over the place. So it's like a case of low bias but high variance. And finally, the best case scenario is of course like this. So this is a case of low bias, low variance. So in this, so when we are combining various classifiers like this, it helps you to that is the original like this way you can actually hope to reduce the variance. I mean, even if the bias is not reduced, at least the variance can be reduced. Now, uh, so 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 there are many multiple ways in which this kind of a thing can be done. So the first idea is of course the simplest, where you have the same training data set, but you just train different classifier functions on it. So that you can always do. There is nothing further to explain in this matter. The second two are the more interesting things, where the classifier function is the same, like let's say a decision tree, but what you will do is you will split the data set into multiple parts, and on each of the parts you will train a different classifier. So the question will arise that how should I split the data set into multiple parts? Will those multiple parts be disjoint of each other, or will there be some overlaps, or how will it be done? So one answer to this question is what you do in case of bootstrap aggregation or bagging. So what is this bagging? The idea of bagging, this is like it's so bootstrapping is a concept in statistics. Uh, like so it's like you are given one set of samples. So that set of sample itself you like you do some subsampling on the basis of it and create another like another sample set of samples. That's the basic idea of bootstrapping. So the idea is as follows. You have a training set of like with n examples, right? N different examples are there. So now you choose n examples of it by choosing at randomly with replacement. That is in the first draw, you will choose one of those examples, but it's not that that example goes away from the original training set. It still stays there. You have just made a copy of it. In your second draw, again you will do the same thing. That is, you will choose one of those the examples in the training set, and you will put it in the selected set, and so on. And you will keep the whole so whenever you are making a draw, the draw will be uniformly at random. That is, all the n examples will have equal probability of being drawn, and this will be process will be repeated n times. So since once or we are choosing an example, that we are basically replacing it. That is to say, it continues to remain in the data set, which means it can be chosen again. So the same example may be chosen multiple times. So just to give a demo, so let us say that this is the like these are the 10 examples which you have from x1 to x10. So let's say that like when you do the first draw, this is the maybe the first three draws. This is what they look like. This is the set of the examples which you got in your first round of 10 draws. So as you can see that certain things are repeated, like for example x5 appears twice, x9 appears twice, but you can see that x2 does not appear even once, x8 also does not appear even once. Similarly, so this is one sample. That is, this is the original sample. On the basis of it, you have created another sample like this, another sample set like this. That like one more sample set you have created on the like this. So and a third one also you have created like this in the same way. So each of these are basically some kind of perturbations of the original data set but they are all different. Yeah, like in this case, like as I already said, x5 occurs twice, x9 occurs twice, but x2 and x8 do not occur. But in this case, you may find x3 occurring three times, but x5 not occurring at all. maybe some x1 also does not occur at all. So if you consider this one, then again some like we see x6 appearing thrice, but maybe x8 never occurring, x5 never occurring, x yes, and maybe x7 never occurring also. Sorry, x7 is there. So x10 is never occurs, right? So, so basically what you have done is you have created multiple copies of the different data set. And what so you can actually work out that in each of these copies, that is about one third of the original data set will not be present in the new data set. That is like on a with some probability based calculations, which I am not going into. You can see that if you consider this one, about one third of the examples have not been selected here. Like x10 is not selected, x maybe x2 is not selected, x8 is not selected. So out of the 10, about 30% have not been selected here. In this case also the same thing. Some 30% have not been selected. Here also the same thing. But there are repetitions. So, so you may wonder that what is the point of doing this, or especially if there are repetitions, then why do we even need or what is the purpose of having the same observations appearing twice or thrice? So we will understand that like maybe in the next class. But intuitively it means that some of the observations you are giving more importance. It's like saying if the same example appears three times or two times, it's like whenever you are building a classifier, you are giving an extra two times or three times importance to that classifier compared to the other examples. I mean to that example compared to other examples, which essentially means if you make a mistake on that example, you have essentially made two mistakes or three mistakes. And you try, and of course, your classifier will try to minimize the number of mistakes. So it will try to make sure that those examples which have been chosen multiple times, it classifies them correctly. Even if it has to make a mistake, the mistake should not happen on that particular example, because its weightage has increased. Instead of being its weightage being equal to 1, its weightage has become 2 or 3. So every mistake on that example will be counted as 2 or 3 mistakes, which the classifier of course does not want to do. So if there are any, so in general, if there are some examples which are very important to you, on which you do not want to make any mistakes, so you will one thing which you may consider doing is simply increasing the weight on those examples. So now what you like basically if you consider this bootstrap aggregation, which I mean the bootstrapping what we considered. So basically we have got k versions of the original training set. So what you can do is you can train a classifier on each of these versions. The classifier may or may not be the same function. Like it's possible that each on one data set you will train a nearest that is for one data set. For this data set you will use a 3 nearest neighbor classifier. On this data set you will train a neural network. On this case you will build a decision tree. That's possible. Or you can the same classifier, maybe you are building a decision tree on this one also, on this one also, on this one also. Both are fine. And then to each of those classifiers, be they the same function or different, you will associate a weightage according to its accuracy on some validation set. So earlier when we are talking about this kind of a weighted voting, so we had assumed that each of the classifiers has a weight associated with it. And we also said that these weights in some sense uh, underscore their reliability, their accuracy. But accuracy on what? As I said earlier also, the same classifier may have very different accuracy on different data sets. So what we will do is so based on this same data set which we have, we will have a validation set also. Just like we are having k versions of the original training set, we will have a validation set also. And we will, so for the validation set, of course, we know the true levels of all the examples. So we will, so all the classifiers that have been trained, all the k classifiers that have been trained, we will ask them to make predictions on the validation set. And based on that, we will get a measure of their accuracy. So those accuracies will define their weights. Okay. So that is the and then once you have done that, then of course you can do the weighted voting as we mentioned earlier. So this process is known as bootstrap aggregation or bagging. Bootstrap is the process of generating the k versions of the data sets, and aggregation is the way of like aggregating the predictions made by the different classifiers of them. So fine. So this is called as bagging. This algorithm which we just mentioned is known as bagging. Uh, yeah. So another thing which I earlier mentioned is that now instead of considering different versions of the data set containing different sets of examples, what we can also do is the examples will be the same, but the features will be different. That is, each version will have all the training examples, but only some of the features. Okay. So here also, like there are, so let's say that originally there are 5 features in the examples that you are considering. So for one version, for the first version, you will again randomly select the different features with replacement. That is, let's say that this is what you get after that process. That is, feature 2 appears twice, feature 3 also appears twice, feature 1 and 5 do not appear at all. In this case also, it's like the same thing. So what is the significance of this? The significance is that in each of the different cases, you are giving more importance to some of the features and ignoring the other features. So it's like saying that instead of consider you are attaching equal importance to all the features, we are like trying to say that some of the features are more important than the others. So of course, if you are doing something like a decision tree, this may not make much of a difference, because anyway, each of the features are going to be evaluated on the basis of how much information gain it is capable of doing. So whether this one feature, say x2, whether it appears once or it appears thrice, its information in each case will be the same. If the information gain is high, then it will be selected. If it is low, then it will be rejected. There is nothing more to say about it. But in some like in case of some other algorithms, this may actually make a difference. It's like where they're like which are based on these like W transpose X kind of things. So here it's like the same feature will be given weights will get 3 different weights or something like that. So it's like effectively the weightage of that feature is going to increase significantly in making the final prediction. Okay, so this way you can like you can do this kind of a thing. Like I mean, you can do the same thing. So you have got different versions of the data set where each version focuses on only a certain subset of the features. Okay, so once you have got the once you have trained the classifiers on these different versions, then what you will do is you will again do the same thing as above. Once these classifiers have been trained, you will evaluate them on a particular on a validation set that you have set aside, or maybe you have created in that like in the same way. You will find the accuracies of the different classifiers on that validation set, and accordingly you will set that weight and then finally do the weighted classification. Okay. Now, of course, you can like what classifier you will choose for this training purpose, for training these individual data sets, that is entirely up to you. They can be the same classifier or they can be different classifiers also. Now, in the special case where that classifier is the decision tree. That is, for each of these data sets, you are using the decision tree classifier. If that's what you are doing, then what you have got is basically a collection of different decision trees. So what's a collection of trees? Obviously, it's a forest. And in this case, since since the features have been chosen randomly, the features used for training the decision trees are chosen randomly. So this kind of a forest is called a random forest. So that's the random forest classifier. And this is like considered to be one of the most powerful or most effective classifiers around. So like as I said earlier, there is no feature, no classification algorithm which is better, like inherently better than the others, but practically we find that there are some features which are I mean sorry, some classification algorithms which tend to do better than the others in on most data sets we come across on real life. That is, for example, for the especially for the task of image classification, it is well known that convolutional neural networks do far better than say something like say uh, nearest neighbor. But uh, like so in most of the practical situations which we come across, random forest is found to be one classifier which is capable of doing of giving good performance in most of the scenarios. It is like among the non-neural network classifiers, random forest is one of the classifiers which in many data sets or on many well-known data sets, its performance approaches that of the neural network. Even though this it's actually based on a like a rather straightforward idea, and you may say even a bit a strange idea that like you are just building multiple versions of the same data set by focusing on different parts of the features. But like if it is like only 5 features and you are making 3 versions of the data set, then probably it does not make any difference. But in most practical situations, you will not have 5 different features. You will have say hundreds or thousands of features. That is, if you are doing considering the image classification task, you might like so if you are considering a say 640 cross 480 image, so each pixel is basically your one feature. So it's like so when you are talking about building a random forest in case of image classification, the different versions which you are talking about basically means different subsets of the features which I mean of the pixels on which you will based on which you will make your prediction. So I will just give a simple intuition of why this is going to work, and maybe in the lab on Thursday we'll probably see a demo related to this also. So let us say that we focus on the MNIST digit classification problem, right? Have you considered have you seen the MNIST data set in any case? No? Okay. So basically these are handwritten digit data sets. So, so every image in the data set contains a handwritten digit. So let us say that this is the image where 1 is written. So like it's like if you consider the pixel values, you will find that most of the pixels are black. However, these few pixels, these are white. The remaining pixels are all black. Similarly, if you consider 2, maybe it is written this way. So if you consider the corresponding image, these features, I mean, these pixels are white, the remaining pixels are all black, and so on and so forth. So now the question is, I have to train a classifier which will predict which image is corresponding to which digit. Okay. So now if you want to classify this image, then obviously you will have to focus on a certain pixels. That is focusing on this pixel or this pixel or this pixel, this pixel, it will not give any use. Similarly, so these are like it's really these pixels vis-a-vis some of the other pixels that you will have to consider. But in this case, the pixels which you will have to consider are maybe these. So if in this case, if you consider say let's say this pixel, this pixel is white in this case, and in this case also it is white. Or if you consider this pixel, in this case, in one case it is black, in the other case also it is black. So there is no point in considering these pixels. But the problem is that a priori we do not know which pixel is going to be white in some cases and black in some other cases, right? We do not know that a priori, and because we do not know it, because the position and the shape of like every digit is going to be different, because remember that it's a handwritten digit. So some people may write 2 in this way, some people may write 2 in this way, some other people may write 2 in this way. So there can be lot of deviations. So focusing on only a particular set of pixels is not going to give you anything, because we will not know which pixel to focus on. So what a random forest is doing is that, like, random forest will pick up some subset of these pixels and learn to make decisions on the basis of that. That subset may not be useful, but then there is another decision tree which will be trained on a different subset of the pixels. A third different decision tree will be trained on a third subset of the pixels, and so on. So if you consider say 100 decision trees, or if you consider a random forest of 100 decision trees, you can hope to cover up pretty much all of the like all pixels in the image. That is the and then if you can combine their predictions, you will probably be able to get the right answer. So this is the reason why random forest, even though like from this example it may look like a strangish or like slightly stupid idea even, but if you like in practical scenario, when you are faced with say thousands or millions of features, then then you can realize the power of this idea. So basically that's random forest, and this random forest is one of the most powerful classifiers around. Now like we consider the idea of weighted training. So like when we are talking about bagging, what we noticed is that some of the training examples are being selected multiple times in the bootstrap datasets. So what does that mean? It means that like as I was telling you earlier at that time also, it's like saying that those examples are being given more weightage than the others. They are being given more importance than the other. So whenever when a algorithm, when a these any kind of classifier is trained, there is a loss function, right? There is a loss function which has to be minimized. So the loss function has to account for these weights when it is being trained. So if a same example is appearing 3 times, it effectively means, as I said earlier also, if a mistake is made on that examples, it is essentially equivalent to making 2 or 3 mistakes rather than one mistake. And of course we want to like minimize the loss function, so we will try to minimize the number of mistakes that I make, and like that. So I have to like account for so basically I mean the classification algorithm which I am constructing, it will not or it will learn to make or avoid making mistakes on those examples. Yeah, so basically it will become an expert in predicting those examples. So even if it makes mistakes on other examples, that on those examples which are repeated several times, it will not make any mistakes. So basically, that's the whole idea of the bagging. It's like saying that this if I train a classifier on this data set, it is almost certain that it will not make any mistake for this example, say x uh, x9 which appears twice and x1 which appears twice. So this classifier, the classifier will get here, will become an expert for these two examples, even if it is not an expert for other examples. So similarly, this one will again be an expert for x3 because it appears 3 times, and also maybe on x, well, whatever, if something appears twice, it can be an expert on that also. So it's like basically we are making the different classifiers which we are getting basically are becoming experts on some parts of the data set. Just like in this case, if you consider the different in case of this tagging of features, basically we are training these classifiers which are each of which is an expert on certain features. It may not, maybe not on other features, but on some of the features it's expert. So basically that is what is happening in this case. Like by imparting different weights to the different training examples, I am increasing their that is, I am making some examples more important which must be correctly predicted compared to the other examples uh, on which making a mistake is tolerable. Okay. So this kind of a situation might arise in various practical scenarios where it is more important to to correctly classify some examples, but it's even if you misclassify some of the other examples. So, so can you give an example of such a situation where it is important to correctly classify some examples, even if the other examples are not well classified? Yes, any example you can give?
Sir, can you repeat your question?
So you have different examples. You are given different examples on which you have to make a prediction. Now, of course, the prediction can be like you will of course try to classify all the examples correctly. But can you mention a situation where there are any practical situation where some of the examples must be correctly classified, even if some of the other examples are misclassified? Can you give an example of such a situation? Have you come across type 1
Sir,
errors and type 2 errors?
sir, for cases like in hospital data set, and if we have to predict the cancer, then if we miscorrectly predict that the patient is having cancer, then the patient might go unnecessary chemotherapy, etc. So in that case, uh, it is not favorable to misclassify that.
And in the other case, so suppose someone has cancer, but you misclassify them that they do not have cancer, then what happens?
Again, that is a problem.
That's also a problem, right? So I guess the example which you gave is in the right spirit, but maybe it became a bit extreme because you considered the case of cancer, like where the treatment itself is is as much as a burden as the disease. Right. So like if we say something like COVID, says suppose someone who does not have COVID is classified to be COVID positive, then then maybe they will have to go for isolation and things like that. But but the other way it is probably more dangerous. That is, if they like if someone is negative, is COVID positive, but you tell that they are not COVID positive, that can create a problem not only for themselves but also for others, because that person will think that they are fine and they will go around and spread the disease among others. So this is one situation where like predict making one kind of mistake is less acceptable than making the other kind of mistake. Or it might simply be that some of these data sets or some of these data points are related to some of the some important or some very critical observations. That is like you the yeah, like it may be that some of these data points are related to some very important persons, and the other observations may be related to common people. So in like for these critical cases, it is absolutely necessary to make the correct prediction, while it's not that we may want to make. For the other cases, we may not want to make a wrong prediction, but I mean, like in these cases, it is obligatory to make the correct prediction. So these kinds of situations might arise. So this is like the idea behind weighted training. So based on these, we can do things like weighted k nearest neighbors or weighted decision tree and so on. So since we have been talking about since we have been talking about decision tree, so let us just consider what a weighted decision tree might mean. So suppose what you have got is as follows. So what I am going to show you are the so okay. So first of all, let us see that in a subpopulation, in a node which you are considering, let us say that there are 7 examples. Okay, 5 of which belong to the class head and 2 belong to the class tail. Okay, like H and T. Okay, if you have to compute the entropy in this case, so obviously there are two classes, 5 7 and 2 7th. So the entropy you will get as 5 7 log 2 5 7 minus 2 by 2 7th log 2 2 7th. Fine. Uh, now, now let us say that I am attaching some weights to the different examples. So let us say that this has weight 1, this has weight 2, this has weight 2, this has weight 1, this has, let's say, weight 0, this example has weight 0, this example has weight 3. Okay, so in this case, if you are considering these weights, then your entropy will become. So instead of just counting the number of examples in each class, you will have to consider count the total weight of all the examples in the class. So now each class has weight 6, 1 plus 2 plus 2 plus 1 6, and tail class has weight 3. Right, so the entropy in this case is going to be plus 6 by 9 log 2 6 by 9 minus 3 by 9 log 2 3 by 9. So you'll see that like I mean this entropy may or may not be, I mean I'm not saying which entropy is higher or lower than which entropy, but the basic thing is that the entropy is now changed. So if we when you are doing these or dealing with these weighted examples in case of a decision tree, then this is how the decision tree algorithm might change. I mean the essentially the algorithm itself will not change, but the way you consider the entropies or calculate the entropies, they will change in each of the nodes. Similarly, you can do the weighted k nearest neighbor also. That is when you are suppose you have like for a given point the the different 3 nearest neighbors you are considering. So suppose they have weights of 1 3 and 0.5. Okay, and their respective class levels are H, T, and H. So if you do not consider weights, then of course you will say that H has got 2 votes, T has got 1 vote, so I will